Okay, so I thought we would do, or I would do a few more examples here in case you would like to see them for the law of sines. Up in the right corner here, you see that we have the law of sines reproduced, which simply says that for any angle and its opposite side, the ratio of the sine of the angle and its opposite side is going to be the same no matter which pair of sides and opposite angles we pick. So the first thing to ask ourselves is, can we even use the law of sines? And in order to fix a number in one of these ratios, we need to have a side and an opposite angle. So the question is, do we have that here? Well, it looks like yes, with angle C and the opposite side here, which is side C, we do have a situation where we can do that. Well, we have two angles, so maybe the first thing we should do is just figure out what B is. If we go ahead and do that, we're going to have angle B is just going to be 180 minus 62 minus 35. We're going to need that angle at some point, and that's going to give us 83 degrees. So I'll go ahead and write that in here, 83 degrees. Now we have all the angles, and then we can just, it's a straightforward application of the law of sines to solve for the other pieces that we need. So what we're trying to find here is A and B. So let's write the first relationship for A. Here we're going to have sine of 35 degrees, which is opposite A. So I'm going to divide that by A. And that's, now here we want to set this equal to the where we have information for, or the pair that we have information for, which is going to be sine of 62, which is this angle of C, divided by C here, which is 7. And then we can just do some algebra to go ahead and solve what we need for. A is going to just be 7 times sine of 35 degrees over sine of 62 degrees. Just got that by cross multiplying and dividing out. And when you go ahead and punch that in your calculator, you get something close to 4.547. So now we have A, and then we just do the same thing for B. This time I'm going to write the ratios the other way and put the sides on top. Because these are proportions, we can flip them. Some people like to put the angles on top, some people like to put the sides on top. So here we have B, so I'm putting B on top, and the opposite angle to B is 83, so we have sine of 83 degrees, and you can see here why we needed to solve for that angle to finish this problem off. And again, that's just going to equal the ratio of C, which is 7, over the sine of C, which is 62 degrees. And here we can just solve that for B similarly, and it's going to be 7 times sine of 83 degrees over sine of 62 degrees. And that's going to, you punch that in your calculator, you get something close to 7.869. So now we've completely solved that triangle using the law of sines. We have A, B, and then we found that missing angle. Next we have example 2, which is an SSA situation. Here we have a side, and an angle that's not included in the two sides. And again, our first check is, can we use the law of sines? Well, it looks like we have a side and an opposite angle here. So yes, we can use the law of sines. And since we know in this triangle that C is equal to 13, it might make sense to go after angle C here first in our law of sines problem. So the first, what we have here is the B, side B and angle B relationship. So we know that sine of 31 degrees, which is angle B, over the length of, or the side opposite that angle, is 8. That's going to be a number, so we're in good shape. And that's going to equal the sine of C, which in this case is still unknown, that's what we're solving for, over 13. So now we can just set that up to solve for sine of C. Sine of C is going to equal, just going to multiply both sides by 13. 13 times sine of 31 degrees over 8. And when you punch that into your calculator, we're going to see that the sine of C is approximately 0.8367 0.694. So here we want to find all the angles C such that sine of C equals 0.837. Of course, we can just pop that into our calculator. C is going to be the arc sine of 0.837. And when you do that, you're going to get 56.8 degrees. But this is one of those situations where we need to think about, are there other angles that in a triangle that could have a sine of C equal to 0.837? Well, yes, when we think about the unit circle, we have to think about the supplement. I'm going to draw a little unit circle up here. 56.8 is right here. Remember, the sine is the y coordinate, so if I'm going to just intersect this with the y coordinate, we have to worry about this one here as well. And that's going to be 180 minus 56.8. So we have to, C could also, or C could equal 180 degrees minus 56.8. And whenever we're working with the sine function, or any trig function, you have to think about the multiple solution case. And that would give us 123.2 degrees. So we have two different possible angles. And that shouldn't surprise us here, because remember, SSA is the ambiguous case, and we either get 1 or 0, 1, or 2 solutions. And it looks like in this case we're going to have 2 solutions. If I was going to draw that on this picture, it'd probably be something like this. Here's the altitude. One case is shown here. That's going to be the one where it's 56.8 degrees. And then the other one would be something like this. Call that C prime. And that's where, maybe I'll just put a little prime here, C prime. And that's going to be the other case we're going to get in this example. So let's just go and finish off those 2 cases. So we'll do case 1 over here in blue, case 1. Well, C is going to be the 56.8 degrees. And if we do that, we know A is going to need to be 180 minus 56.8 minus the 31 degrees that's given there. And so that's going to give us 92.2 degrees. And then we need to just solve for A in that scenario. And we know that A over the sine of A, which is 92.2 degrees, is going to be equal to 8, which is B, over the sine of 31 degrees. Again, just straightforward law of sines application here. If I cross multiply, A is going to be 8 times sine 92.2 degrees over sine 31. And that's going to give me 15.5. So the first triangle is going to have an angle A of 92.2, C 56.8, and a side A of 15.5. Case 2, we're just going to do the same thing, except now we're going to start with C equal to this one. Maybe I'll do that one in green, or at least finish it off in green here. So C is going to be 123.2. That's this one here. Maybe we'll call that C prime again. A prime in that case, we have a different angle here. A prime is just going to be 180 minus 123.2 degrees minus the 31. That's going to give us 25.8. So now we've gotten that piece, and then to set up the law of sines again. A over sine of A, which in this problem will be, or this case I should say, is 25.8 degrees, over the same 8 over sine of 31, which is the B side and the B angle, and A will be 8 times sine of 25.8 degrees over sine of 31, which will be 6.76. So those are the 2 triangles we'll get. I thought maybe it might be helpful to show how that same problem can be solved with this GeoGebra tool. And so I've just pulled up the applet, and this is the default, just like we showed in class today. So the first thing is, in this example 2, I think the angle was 31, so I'll go ahead and make that angle 31 degrees. and then the side adjacent to that 31 was on the bottom there, side of 13, so that's B. Let's slide B down here to be 13, and then I think A was given in that problem to be 8. So this opposite, the side opposite 31 was 8. And we can see here, again, remember, if A is too small, if it's less than the height of that triangle, we're not going to get any, or less than the height of the triangle you would make, we're not going to get any triangle that can be formed in this ambiguous case. But in this case, it is 8. So 8 is bigger than the height, but it's smaller than that side B, which is what creates that situation of two triangles here. And we can see that if I go ahead and show SSA solutions, we have 56.8 as one of the answers. I think that matches with what we had before, and then we had 123.2 is the other angle that comes out of that. So we can see that the GeoGebra applet also matches the algebra we just did. And then finally we have an ASA situation, angle, side, angle. This is a relatively straightforward one. Can we use the law of sines? Well, when we look at it at first, it looks like we don't have any angles in opposite sides, because this is A is still a variable. The angle opposite 9, which is the only side we're given, is not there. But this is a situation where it's really easy to go ahead and find that other angle, because all the angles add up to 180, as we know. And so this is going to be equal to 70 degrees, which is just 180 minus 76 minus 34, the other angles. Once we go ahead and do that, we now have an opposite angle side pair that we can use to solve this problem. So that's what we're going to go ahead and do. For the first one, we'll find side B. So we just have B over sine of 34 degrees equals 9, which is side C, over the sine of 70 degrees. We'll go ahead and solve that for B. That's just going to be 9 times sine of 34 degrees over sine of 70, which is going to be about 5.36. So that's what B is, 5.36. And then we go ahead and solve for A. So A over the sine of 76 degrees, which is this opposite pair, is going to be equal to 9 over sine of 70. Solve that for A. 9 times sine of 76 degrees over sine of 70 degrees. And that's going to give us about 9.29, which is what A is. And let's just see if this passes the reasonableness test as a final check. Well, our largest angle in the triangle is 76 degrees, and it sure does look like our largest side is across the largest angle, 9.29. Our smallest angle in this triangle is 34, and the smallest side of B, 5.36, is across from that. So that's at least one quick reasonableness test you can do when you solve these to make sure you didn't make any careless errors in the problem. And so here we have those pieces of information.